Hello and welcome to Physics 2 Lab 3 Circuits. My name is Joshua Smith. Introduction. The purpose of this lab is to use physical principles of energy and charge conservation to predict circuit behavior involving resistors, capacitors, and multimeters. Preview of our results is we found that real-world circuits do not perfectly follow the ideal physics principles, for example, the loop rule, but we can use them to guide our predictions. We also observed that charging and discharging a capacitor is dependent on time. For the system, for both experiments, the system is every electrical component that makes up the circuit. So basically the circuit itself and surroundings for both experiments, it's everything else that is not the circuit. So like the air, table, people, all that. Some fundamental physics principles is one, the law of conservation of energy. Energy cannot be created or destroyed, only transformed. This law is the basis for, well, these laws are kind of the basis for the loop rule and node rule. The law of conservation of electric charge is that charge cannot be created or destroyed, only transferred. And the loop rule is that the potential difference around the loop all adds up to be zero at the end. So the total potential difference will be zero. And node rule is that for any node on the circuit, the current going in is going to always equal the current going out. Ohm's law is V equals I times R. It describes the relationship between voltage, current, and resistance. And the change in voltage for discharging an RC circuit is this formula, which will be important for our second circuit. And then the potential difference across a battery is the electromotive force. Conductor would be I times R, and capacitor would be charge divided by capacitance. So here are the initial conditions. To spare time on this, I'm not going to read them all out, but they're all here. So we collected data. We found it to be 15.6 and 15.4 milliamps, which are about the same, so that's good. When we reverse the leads, we get the negative values. Here's a picture of our circuit, and here's the diagram for it. And then when we converted one of these to a voltmeter, the ammeter stopped reading current because the multimeter in voltmeter mode has a very high resistance to accurately measure the potential difference, and due to this high resistance, electrons stop flowing and the current becomes 0 milliamps. For 2.4, we measured the potential differences across the batteries and the two resistors to get these values, and we summed them all up, and we ended up getting almost 0 volts, which is close to what would be the truth for the loop rule. But kind of the reason for this is likely due to the limited precision of the multimeters or resistance in the wires, because wires can't be perfectly no resistance. Then here's a graph of it that kind of goes with our potential differences. And then when you attach the voltmeter, you alter the circuit. Why doesn't the ammeter reading change? This is because the voltmeter is attached to the circuit parallel, and because of its high resistance, the current is going to keep going along the original path. Therefore, the ammeter reading does not change. And as you can see, ammeter is going to be the same. And replacing the voltmeter with the ammeter in parallel, the ammeter reading goes up because now it has a path. Now the circuit has a path of less resistance, so it's going to go through the ammeter instead. So it's going to lower the overall resistance and lead to a higher amperage reading. Here's some calculations for the different resistances. Total resistance is going to be around 148, 49 ohms. Then observe the behavior. Now to the RC circuit. Observe the behavior of the capacitor charging. The bulb lights up dimly and goes out very soon. After a bit, it gets really bright and decreases in brightness over the course of 15 seconds and goes out. And then for this, the bulb starts lit up when the capacitor is charged. Then the bulb slowly dims and goes out when it is discharging. And here's the kind of the charge times. We did 3 minutes and 30 seconds to really ensure that it was charged. And here's some assumptions we did that lead to possible sources of error. And then here's the final questions. What if you charge a capacitor with no resistor in the circuit? So this would be an ideal model, and it would predict, and in an ideal model, there's like no resistance and stuff that isn't a resistor. So with zero resistance, the ideal model would predict that a capacitor would charge instantly as there's no impedance to electron flow. And this would not happen in real life as components can't have zero resistance. It's just not possible. Then for this final question, we predicted our RC, our time constant, to be 10 seconds, and the time to fully charge the capacitor is about 5 times that, so we predicted about 50 seconds, but we did 3 minutes and 30 seconds to really ensure. But regardless, the measured time is much longer than the predicted time, likely due to bulb resistance being inaccurate, human time error, and or multimeter imprecision.